You are welcome to today's class, and today we want to solve questions on fault analysis, and we want to basically look at questions on unsymmetrical fault. Unsymmetrical faults. So we have gone through unsymmetrical faults, and we know how the positive phase sequence, negative phase sequence, and zero phase sequence come about. So let's start with the first example on fault analysis. So let's say we have a three-phase system. A three-phase, three-wire system has a normal voltage of 10.6 kilovolts between the lines. It is supplied by a generator having a positive. So we have a generator, and the generator has a positive phase sequence, a negative phase sequence, and a zero phase sequence. The positive phase sequence is 0.6, negative phase sequence 0.5. These are reactances, so you don't forget to bring the G's, 0.2. And basically, we are supposed to calculate the magnitude of the fault current which flows when a line-to-line fault occurs. So let's say this is the terminal of the generator, and we are saying the fault has occurred here, but the fault is a line-to-line fault. It's a line-to-line fault. So I think that's the basic idea. It's a line-to-line fault. So we know that when there is a line-to-line fault, basically we put the PPS, which is this, X1, and then the NPS X2. We connect them like this, where here is I1 and here is I2 as discussed. And we basically know that I1 will be equal to E over X1 plus X2. Then our fault current, we have discussed that is J root 3 I1. Depending on whether you are taking these three phase faults, phase A, phase B, phase C, we are saying that there's a line-to-line fault. So the fault current is either IC over, or the fault current is either IB, and we are proving that already. And basically, if you take that to be IC, the fault current is J root 3 I1, or it can be minus J root 3 I1, it doesn't matter. So with this case that we have, the power system has a voltage of, let's go back there, it has a normal voltage of 10.6 kilovolts between the lines. So we know this is a line voltage, and we know we are going to do the calculation with the phase voltage, right? So here is 10.6 kilovolts, but don't forget that you divide by root 3 to get the phase voltage. Then we have X1 here and X2 here. Now X1 is giving us G0.6, G0.6, and X2 is giving us G0.5. Now notice that during line-to-line faults, we basically have only the positive phase sequence and the negative phase sequence. Because the fault is not to ground, the zero phase sequence value, we are not going to deal with it because the fault is basically a line-to-line fault and there's no ground. So we are not going to deal with zero phase sequence. So from this, we can easily find our I1, which we have already said is E X1 plus X2. So my E is 10.6 times 10 power 3. I divide this by root 3, which is the phase value. And my X1 is J0.6 plus J0.5. And when you calculate this on your calculator, I'm going to get minus J5563.56. This is I1. And since our fault current is J root 3 or minus J root 3 I1, doesn't matter. So J and then root 3 I1 is now minus J5563.56. So a point that can easily find the fault current to be 9636.37. Basically, you found the fault current for such a simple question. I hope that was clear. It was a line-to-line fault, only positive phase and negative phase. And we know the system will be connected like this. So we just fix them as needed. So we are not going to use the zero phase sequence value given because the fault is a line-to-line fault. So basically, this will be the solution to this question. Let's look at another problem. Let's say we have a three-phase example 2. We have a three-phase generator and it has its neutral earth through a 3 ohm resistor. So we have a generator here and we are saying that it has its neutral point grounded through a reactance. It's a zero point 0.3 reactor. So you know it is G 0.3, right? So it's G 0.3. And then we have it connected in parallel with another generator. And that generator has isolated grounding, right? It's isolated. It's in parallel with another identical generator having isolated neutral. So isolated neutral means it's not grounded, right? That particular one is not grounded. And each generator has a positive sequence reactance of 1.2, a negative sequence of 0.6, and a zero sequence of this. So what it means that, let's say this is generator 1. So generator 1 has x1, x2, and x0. x1 is giving us J1.2. Let me have that written out in a very nice place. Let's have our network drawn nicely, maybe at the next page. So let's say we have a network here and another network here. So here is a star grounded with a reactance J 0.3 grounded. And then we have a second generator like this. This is G1, this is G2. They are connected in parallel and a fault occurs here, right? So the X1, X2, and X0 for the generator are given by this, and the X1, the X2, the X0 of this generator are also given. So when we look at this, the X1 is J1.2, this J0.6, and this J0.9. So I want to have that there. J1.2, 1.2, J0.6, and J0.9. So these are, and it said the two generators have the same values, right? So this one is J1.2, J0.6, and J0.9. And we say a fault has occurred here. Let's look at the type of fault. Now, each generator has a line to neutral voltage. That's a phase voltage of 5850. So we know that basically V phase has been given as 5850. So let's note that. Now you realize that all these are already given in ohms, right? You know, basically if they are all given in per unit, that's when we would have, like the example we just solved here, you realize that we are using the terminal voltage given us because all these were given in ohms. So we continue using the ohmic values, right? And then in that case, you have to use the terminal voltage. If they were given in per unit, I would have used E as 1 in the calculation. So note that. Yes. So this one too, everything is given in ohms. So I'm going to use the phase. Here, I've been given the phase voltage already. I don't need to divide by root 3. Now let's look at the type of fault that has occurred. It said a line to ground short circuit occurs on the common bus of phase A. So what it means is that when you look here, here is a line to ground fault that has occurred. It's a line to ground fault. And we know in our calculation that if I have a line to ground fault, I basically need the PPS value, the NPS value, and the ZPS value. And I'm going to connect them in series as we have learned. So this is the PPS value in series with the NPS value and in series with the zero phase value. And in case the fault had a resistance to ground, I would have inserted it as part of this, right? And from this, this is I1, this is I2, this is I0, and I1 is equal to I2 and is equal to I0. So basically, I0 is given by E over x1 plus x2 plus x0, right? And then we have proven that our fault current, when it is a line to ground fault, is given by 3 I0. So we basically need to know I0 here. Come and fix that here to find IF. So let's do the fix. But before that, we need our x1, x2, and x0 value. So we come to our diagram This is the network that we have. This generator was given that it was isolated thing, right? So that one was isolated. So now let's see how our PPS value is going to be. So I have two generators, right? So PPS, don't forget that we need to break our terminal voltage. Then because they are in parallel, I have their reactances in parallel like that. This for generator 1, this for generator 2, and then there's a fault at their terminal here. So here, this was given as J1.2, here too is given as J1.2, and this E is given as 5850. So basically our X1 will be this and this in parallel, which will be J1.2 times J1.2 over J1.2 plus J1.2, and X1 will basically end up being J0.6. This is our PPS value that help us to get X1. Now notice that how we are finding the X1, the X2, the X0 does not depend on the type of fault. No matter what fault it is, we are still going to go about the same process to find X1. So let's find the NPS. The NPS value 2, we draw a line. Here we don't bring the voltage source. So I bring the reactance of generator 2, the reactance of generator 1, they together, and then there is a fault. Here too is J 0.6 given, here too is J 0.6. So I can see that here too, X2 is in parallel. So J 0.6 times J 0.6 over J 0.6 plus J 0.6, and I'll get my X2 value to be J 0.3. So I have my X2, I have my X1 that I need in this question. So I'm just left with X0. Now notice that X0 depends on the grounding system of the problem. So now generator 1 is star grounded with a resistance. Generator 2 is isolated. So let's note that with a reactance, right? So Z0, we know we draw a line, and here we have two things in parallel. So let me have that parallel system. Now generator 1, it has a reactance, and you see, because it's star grounded, I'm going to connect it to this line, and I'm going to bring the reactance, basically going to bring the reactance of the generator. And now because the generator also has a reactance to ground, we have already proven that we need 3 times of this reactance where the generator is. And this only appears within the zero phase sequence calculation, right? So here was given as J 0.9, and we need 3 J 0.9, and we need 3 times the J 0.3 to be added, because this was given as a reactance, not a resistance. So it's J 0.3. So 3 times this, I'm including that in the zero phase sequence for generator 1. Now, when you look at generator 2, it is star ungrounded. So I'm not going to connect that to the line. So I'm going to leave a space before I bring the reactance of generator 2. And that value 2 was given as J 0.9. And the fault is here. Now, because here is open, basically the fault current is basically going to go through this. So it's going to be this and this in series. So X naught will end up being J 0.9 plus J 0.9, right? Because this will give me J 0.9. So X naught will happen to be what? J 1.8. So now that I know I basically know my E and my X1, my X2, my X naught. I'm just going to fix them in the series circuit. E, the phase value is already 5850. This is J 0.6. This is J 0.3. That's what we got for the negative phase, and J 1.8. So this was J 1.8 X naught, J 0.6 X1, J 0.3. I bring them as required. This is already a phase value. So my I1, which is E over X1 plus X2 plus X naught, will end up being 5850 all over J 0.6 plus J 0.3 plus J 1.8. And this is going to give me I1 or I naught. We are using I naught. I1 is the same as I naught. So this will basically give minus G2166.66. So this is my I naught, and my fault current is 3 times the I naught. So this will be 3 times minus G2166.66. And I'll basically go and get minus G6500. And in terms of magnitude, I get 6500 angle minus 90. So in terms of magnitude, the fault current is 6500 amps. Simple calculation, right? So we'll end here with the second example. In the next class, we are going to look at more examples on fault analysis. So thank you for listening. All the best.